Cool. Great. All right, let's begin. Thank you, people, for joining us in the room and also online. It's my great pleasure to have Lennert De Smet, PhD student in neurosymbolic AI from KU Leuven, under the supervision of Lennert De Smet. And Lennert's PhD is revolving around how can we build neurosymbolic systems that comprise a subsymbolic part, a neural network, and some symbolic part. How this part can interact together, be scaled together on larger domains, and deal with the intricacies of real-world data. So in previous works that Lennert showed us, because he was already visiting us, he was dealing with, for example, combining discrete and continuous variables and having constraints over both, right? And this time, I think now the focus on sequence modeling. And how can we have neurosymbolic systems where we have these sequences, but also we want them to be interpretable, intervenable, generalizable, right? Lennert, the stage is yours. Thank you.
Thank you for this introduction. Let's see if I can change the slides. Yes. Well, thank you for being here. This will be a presentation about the latest work I've been involved with, that I did together with my fellow first co-author, Gabriele Venturato, published at AAAI a couple of months ago by now. And well, without further ado, let's jump straight into it. So imagine you have a data set of sequences, a sequential data set. In this case, maybe some trajectories in a game, you're interacting with the game, and you know the actions that connect the different images one for the other. And you would like to train any sequential model to generate these sequences again at test time. So you want to give it a set of conditioned actions, right, down, left, up, left. And you want a generation that ideally follows exactly those actions that we give. So it seems to be a pretty simple task. And of course, we have very powerful sequential models. So let's plug in, for example, a deep hidden Markov model, which is just a Markov model with some neural components in there. You give it the same conditioning, and what you get is, I hope it's visible, but the agent is sometimes a bit in superposition. Even if you consider the most likely spot, it's not always logically consistent, and also doesn't seem to follow the actions all that well. Now then you might say, why do you use a Markov model? Use a transformer, much better. Turns out it's not that much better. The generations are maybe more crisp, but it tries to find this way around putting the agent in a spot where it has to be by just putting more agents, and even then, it's definitely not what we want. So this is a bit puzzling because the logic here is super simple. The action of taking an action up, or the effect of taking an action up, is just incrementing the agent's location with one. So how can these models not learn this? And even if we then have the knowledge, can we not just give this knowledge to the model so that it can use it at learning and test time? And this is supposed to be what neurosymbolic promises. You take neural networks and you take a logical background knowledge, you add the two together to make the neural networks follow that knowledge. Why? Because you can encode it precisely in the form of logical formula. For example, coffee implies happiness. If you put this on top of a simple classifier, then the classifier would follow the rule that if it predicts coffee, it also automatically has to predict happiness. So why don't we use neurosymbolic models? Well, currently, none of them scale to these sequential domains or any large domains in general. That's the biggest bottleneck of neurosymbolic right now. And so that's also what we try to solve here in this work. These proposed neurosymbolic Markov models are supposed to combine the sequential modeling capabilities of what we already have with the symbolic logic of neurosymbolic AI. Since I will not assume that everybody knows neurosymbolic, I'll give a quick primer, starting from Bayesian networks. So in a Bayesian network, if I show you this, everybody knows that you have two variables, P and M, for player and a monster. And there might be some dependency between player and monsters and being hit. So H is the player is hit by the monster, and that dependency is encoded in the conditional probability tables. So what you do in a Bayesian network is you define these CPTs to define your knowledge in a sense. On the right-hand side, you have probabilistic logic, and there you use a logical language to define those same dependencies. At the top, you have, again, a player variable and a monster variable with some probability of being at a certain location. And you have one rule that encodes directly what the effect is of the player and the monster being at the same location L. And the same machinery of probabilistic inference still applies. You can compute the probability that hit is true which is 0.45, but just multiplying those probabilities. So left you define CPTs, on the right you define logic programs, and you can take advantage of the automated reasoning capabilities that we have for logic. Now this is, or that was not neural yet, no neurosymbolic. So what we do, we just add neural parameterizations to everything. So we get deep Bayesian networks that take maybe an image, and from that image predict the probabilities of the variables. On the probabilistic logic side, the same thing happens. Instead of having the numerical probabilities, you just give the output of a neural net, and the same inference techniques apply. But here you can also see why neurosymbolic does not really, or has difficulties with scaling, because it's performing probabilistic logic inference that's sharply hard, and that's the same as counting the number of solutions to an NP-complete problem. So that's why it doesn't scale well. And what do we want then? Well, if you look at Nessie, or if you want 5 properties, they have to, or your models should exploit sequential dependencies to scale to sequential situations. Relational, discrete, and continuous are also something you want, because relational means you encode logic. The logic should have an effect on the neural networks as you want it, and it also should support discrete and generative tasks. Now, Nessie supports a couple of them. Looking on the probabilistic side, you have HMMs that support a couple others, and ideally you want both, and that's what we're going to discuss today. And I'll go through in 3 points. Scaling, so a bit at the technicality, so please bear with me. Once we go through those technicalities, though, I'll look at the real properties that make these models interesting, and then I'll give a bit of an outlook to what the impact might be in other more challenging applications. Let's start with the internals a bit. So if you look at what is out there in the probabilistic side of things, then if you have a Markov model, the simplest you can do is take a particle filter. Just as reference for our NSCMM here, all the x's would be a combination of S, the symbolic states, and N, the neural states. So if you take a particle filter, what happens is it's a recursive process. You first sample from the recursive distribution, fine. You transition those samples to the next time step because you have the transition probabilities. And then finally, because you need to satisfy this evidence variable Z, you resample, or maybe first you weigh the transition samples with the evidence, and in practical cases you resample, so that you have a set of samples that is now representative of the T+1 time step. Now what is problematic here is that this is fine for inference, but in neurosymbolic we need to do learning. Any of these probabilities can have a parameterization. You can see it by the index phi. So those should get some gradient information, so we need to differentiate through it. And that's a problem because in this filtering approach, the resampling step is a sort of discontinuous operation that is not differentiable. You can see it as sampling from the set of discrete samples you have and picking a new set that is better. There is no gradient through that. The partial solutions exist if you just look at continuous domains, plenty of literature out there. But if you have both discrete and continuous, things become hairy again and harder. Good, so that's the problem we're solving now. We want to get differentiability and learnability for discrete and continuous neurosymbolic. How we tackled that is we looked at not particle filters, but Raoult-Blackwell particle filters, and that's nothing more than a fancy name for one simple change in the methodology. Namely, instead of having this two-step transition, then resample, you just immediately transition what you already have according to the conditional transition probabilities. And that's it, that avoids resampling, everything is okay. Even more, since you have these exact conditional probabilities, you can apply a whole range of discrete gradient estimation techniques, anything you like, reinforce if you've heard about it, or any others. Most of them directly apply since you have these probabilities. So we have differentiability and everything in a sense is now okay again with the model. Now you might ask immediately, why do you not always use these Raoult-Blackwell filters then? Well, what makes them, if they are so much better, what is the problem? And the problem is in the fact that you need these exact probabilities. Computing those can be hard and, well, is often hard. So there is a bit of a trade-off. You get differentiability, everything works, but you still need to do some hard computations at some point. Now, in many practical applications, it turns out that it's possible, but it is definitely a limitation. And of course, we also do our very best to avoid or mitigate this problem as much as possible, exploiting dependencies, factorizations, putting everything as much on the GPU as possible so that we get it to work in practice. Good. Technicalities aside, let's now see what these things can actually do when you apply them in practice. And I will look at three properties. First, how logically consistent or more consistent are these NESIMMs? You have this nice property of intervenability, which I will talk about, and then also in terms of generalizing capabilities, what can we see there? So we'll go back to the data set from the beginning. Exact same case, sequence of images. You want to generate those images in your model. So you have a model, condition. Now you can also, at least if possible, add the knowledge you have. And again, I want to emphasize that the knowledge is super simple. It's just a couple of these rules saying if you take the action up in the previous time step, your agent location will just increment with one in the y direction. Same for all the other actions. And that's it. You want to generate, and as we've seen before, plugging in transformer with no knowledge because you don't have the ability to add it, you get garbled generations. Same for the deep HMM. Things are all over the place. In the NESIMM, you add the knowledge, you have the capability, and that really does allow for logically consistent generations. Question?
So when they got an experiment set up here,
yeah.
So with the transformer and the HMM, are they also trained with these conditions in mind? And then just kind of generalize? Or?
Yes, so for the people online, the question is, are the non-neurosymbolic models trained with the same conditioning in mind in the setup? And the answer is yes, so they should be trained exactly with these conditions. So the context of the transformer, for example, is the given actions, the given conditions. Yeah, and same for the deep hidden Markov model. Yeah. So we try to equalize the setting as much as possible. Good. Of course, you might say these are just images. You might have cherry-picked them, and that is partly true, of course, because I need to show how good they are. But we can also really quantitatively show that these models are really logically or worse at logical consistency. And for this, we look at reconstruction accuracy, and the setup here is you give a sequence of models. For these sequences, you know exactly where the agent is at every time step. You ask the models to reconstruct the same sequence, and you use a classifier to then check are the locations in your reconstructed sequences the same as the ones that they should be. And they have to be because the transitions are here deterministic. And so if you compare these two, you can see how well, even for reconstruction, are these models at following the logic or following the rules of the game. On a 5-on-5 grid, so you saw the empty room before, it's a 5-on-5 grid. The transformer does pretty well, not too bad. Only the deep HMM is worse. But when you then generalize to 10-on-10, so this is training on a different data set, different setting, there they start to really bring down slowly over time. So they're just not able to keep the consistency of larger grids, it seems.
You need testing on different things.
Sorry?
You need testing on different things or training on different things?
So for both these cases, the 5-on-5, it's training and testing on 5-on-5. Okay. And 10 is also training and testing on 10-on-10. Yeah, so we don't try to generalize from 5 to 10. Yeah.
How big are these data sets?
Oof, I would have to look at it again. I think a couple of thousand sequences. Yeah. Order of thousands in any case. Yeah. Okay. And then, in my opinion, the coolest property of these models is since your internal representation of these NESIMMs is relational, it's logic, there is nothing preventing you from changing the knowledge at test time. So let's say you go to the next level in your game, and in this level, it's very important for some reason to not go in the last 2 columns of your world. You can simply write this down in one rule in your logic program, add this to the model, and ask it to, again, generate sequences. And as you can see, it actually follows it. And this point, or this case, is especially interesting because the model decided to initialize the first state where the agent is in the middle, but the first action that is given is go to the right. That would put it in the unsafe position. No problem. The logical reasoning figures that out and just says, well, I have to stay where I am then because otherwise I violate the constraint. And then afterwards, the agent goes happily along, just following the actions as before.
And the model, I mean, you could have chosen already the T, right, to go down from the very beginning.
Yes, yes. So you could have not asked it to do the right action. Of course, here we want it because we want to show that it indeed doesn't go into the unsafe area. Yeah.
No, what I'm trying to say is that, so the behavior, expected behavior is that when the action you're asking should violate the constraints, the expected behavior is not to do any action.
Yeah.
Okay.
Yes. Yeah. So there is if there is no possibility of doing a correct action, it should do nothing in a sense.
Correct.
Yeah. And maybe also an important point here is, in case you want to do something similar with any of the other sequential models, you would have to retrain them on a data set where avoiding the last two columns is present, because these models have no way of changing at test time. They are based on training and changing in that way, according to a different setting. Okay, that was our generative experiment. Now we want to look at generalizability, and for this we look at a very simple discriminative task, namely, again, a sequence of data. This time the data is symbolic though, so I'm showing the images, but the data that the models get is a symbolic representation, meaning the exact location of the agent. For example, at the beginning, it's given as the agent is at 4-1, and so on. What else do you get? Well, you still get the actions that the agent is taking or should be taking. And you also get an observation of whether or not the agent is hit by a monster. Because in this environment, we have a couple of monsters running around. The agent also runs around. To then, at the final, or across the sequence, the supervision you get is, okay, looking at the sequence, is the agent now dead at the end or not? Is it still alive or not? That's the label that we need. So for this model, now it would get a symbolic state, no images, but symbolic. You condition it on it. The knowledge is a little bit more complex, but still reasonably easy. And I would say the important part is here in the final rule, because here you define when the agent is hit, meaning the agent is hit when it's a distance of 1 apart from an enemy. Now, the attack of an enemy is not deterministic. It can fail, it can miss the agent in a sense. And the learnable components are also these two things, because what we assume here is we know exactly how the agent moves, which makes sense. If you play a game, you know how you behave in the environment, but you don't know how the enemies behave. And that is what is being learned by a neural network, the behavior of an enemy, how the enemy approaches killing the agent. As well as this little parameter determining the chance of hitting the agent. Good, and then of course the prediction that it should get is dead or alive. You train these models. And let's now look at the dimension of generalization in different cases. This is the training case, so we have a 10 on 10 grid, 10 time steps of sequences, and only one enemy running around. And since this is nothing more than a sequence to binary classification, you would expect all these models to perform pretty well. There is some uncertainty, but the models should perform reasonably well. And you can even see that the transformer is outperforming everybody. Now, what happens if you move to 2 enemies? Then balance shifts around a little bit already. Maybe not the biggest change ever, 1 or 2 enemies, especially since they are kind of weak enemies. But what if we increase the number of time steps, the sequence length? That really shifts the data distribution quite a bit, because you might see the agent dying more often since it's running around in the environment for a longer time with more enemies. And in this case, also the transformer really does not or stops working quite significantly. This is balanced accuracy. So a 50-50 is still the baseline of random choice. This seems to be a pretty hard setting in general, though, also for the other models.
Yeah. So in this case, you train on 10 by 10 with 20 steps.
No, so this is important. This is really generalizability.
Okay, so you just train from the original one?
Yeah, training happens here for all the models, and you just evaluate them on the other settings to see, can they, without retraining, generalize to these other settings? Or, in other words, are the representations that the models learned robust to change in the environment? And we have one more, namely just increasing the grid size. Here, the deep HMM is not shown because it's not applicable. It needs a fixed grid size for its transitions to work. The others do not need that because everything is internal. And there is the same average conclusion holds. In general, or on average, the NESIMM seem to be a good trade-off in generalizability and more robust to changes in the environment.
The intuition why then the 20 steps of deep HMM comes better.
For the deep HMM, not really. So also the question, if I have any intuitions whether for the step from 10 to 20, why the deep HMM might be better, and my answer is still no, I don't have any intuition, mainly because everything is really hidden in a latent, or in a latent state as well, so I couldn't inspect those as well. Also because the transitions here are neural transitions, I cannot really see specifically what happens, so no. I imagine it's a bit more robust because it's using the Markov property, so it has to base its predictions on just the previous step, which is a limiting factor, and limiting is often can lead to a bit more robustness, but that's the only thing I can say. And one final note is that these final two settings, especially for neurosymbolic AI, are really non-trivial. You cannot apply easily, at least, a neurosymbolic system in these cases. 20 steps and 15 on 15 is really quite a lot of possible trajectories that you, in other systems, would have to exploit or look at almost exactly. Okay, and then finally, a bit of an outlook, seeing what NESIMMs can do for language generation and safe reinforcement learning. Starting with an example of what we want an LLM not to do. Let's say I was bored, so I can ask the LLM, what is the difference between a cat and a dog? And the answer it gave me was, both are domesticated carnivores, but cats are smaller than dogs. Now, you're also all very smart people. You can come up with an example or a counterexample to this, namely silly LLM. You're obviously forgetting about the chihuahuas. They are smaller than cats. You're wrong. What you do not want to happen is that the LLM starts to be very frustrated and verbally attack you in a not pleasant way.
Is this really happened, or is it?
Part of it happens. The profanity is definitely not there because it is hard to get models to do this, but you can get them to do this. In any case, we want to avoid this. Now, this is not an easy task because these state spaces of LLM generation, if you look at them, well, there are hundreds of thousands of tokens that the probability distribution is defined over. And the tokens are tokens, not words, so they can, in a combinatorially many ways, lead to construction of profanity that you have to, in a sense, all check. And so other approaches have been looking at this on the angle of, well, let's just optimize for safety, for well-behavedness, which might help a little bit, but you don't have any guarantees. And I don't have children, but if you have children and you want them to interact with this LLM, probably one of the basic things you want them to do is that you're guaranteed to have no profanity in whatever they generate. So just training will not be enough. There are other methods that use sort of search combinations to alter the predictions of the LLM to also avoid this and get more guarantees. But then what kind of distribution are you really looking at? What influence does it have on performance? It's all not that clear. You also don't really want to retrain an LLM for different test cases. Ideally, you just want to give new constraints and it should work. And that's how we then come to how NESIMMs might augment LLMs with those capabilities. You have to construct first a Markov model, but that's pretty easy. Although it's easy, but I forgot one error. So you take the context, it's just C0 at the context at time 0. You take the initial token, call the LLM, you get the next token. Context is updated, and I missed the error between P, I, and Ci plus 1. Sorry for that. In any case, you can write it down as a Markov model that works out. And then what you want to ask is, what is the probability, according to the LLM, of predicting these tokens, given the context and the previous token, but then also a certain safety specification. A specification that you want to check at least H time steps, a certain horizon in the future, so that you can guarantee, okay, in the next H steps, profanity should not occur. And that probability distribution is what NESIMMs approximate in an unbiased way, so you have that guarantee, or at least that statistical guarantee, and you also get the flexibility that we talked about before. Now, for reinforcement learning, you also have many cases where you want to have constraints hold, especially if you train agents in the real world. During their exploration and training, they should probably be a bit more careful than if they would be trained in a simulation. Back to my favorite game that we've been using. On the left, you don't want the agent to go to the right into the lava. In the middle, you probably don't want the agent to go to the monster. And on the right, it's not as much about safety, but more about constraints. Namely, that the agent should just simply never try to open a locked door if it doesn't have a key in its environment. Those are things that in traditional reinforcement learning, you would have to try to encode in the reward, which is not an easy thing to do. And here you could just program that behavior into the agent. Now, in our group, we have worked on this before, programming these safety specifications in a logic program, and then taking a neural policy and conditioning it on this specification. But that had the limitation that it used exact inference still, strong guarantees, but not scalable, and it only looked ahead one time step. So it's pretty clear what NSCMMs can then do. They approximate these condition policies over time, so you can check constraints over a certain number of time steps in the future, while still adhering to the constraints. Good, and that's it. So as a final conclusion, the goal or main goal of these NSCMMs is really to augment neural networks with the guarantees, or with certain guarantees that they adhere to the constraints that you want them to adhere to. We try to keep things as scalable as possible to make sure that you can really combine neural and logic and probability theory all at once. There are some trade-offs there, of course. But nonetheless, these models have cool properties. They are more consistent, more generalizable. You can intervene on them as well. And in the future, we hope to. I cannot share much today, but we are working on these other applications, and yeah, they have some promising results for now, and we hope to share more of that soon as well. And then all that's left is me to thank you for your attention. Thank you. And I would be very happy to answer any questions, of course.
Questions?
Emil?
Thank you so much, Nick. Could you explain a bit more on this stronger setting? The kind of data that is trained for the output.
Yeah. So let me go back to those slides. Good. So the input here is the game state at the beginning, meaning the exact location of the agent. You get a series of actions that the agent will follow. Let me think, because it's been a while. I do not think we give the location of the monsters, so we don't assume that the monsters are known, have known locations.
We give the images.
We do not give the images in this experiment.
That was a train.
So the data, in a sense, is just how to say. I don't like to use the word symbolic too much, but they are the exact representation of the exact representation of part of the game state.
So you don't need this training on the highlights?
No.
Okay.
So that's the change, and the reason why we did this is if you would give images, in the case you move to environments with two enemies instead of one, you would need a neural network that is able to also suddenly generalize from predicting one enemy to predicting two. So you need a sort of relational predictor, and there is just not much out there in terms of relational object detection in a sense. So that's why we just stick to good old-fashioned symbolic complete representations.
How do you turn that into text to feed the transformer, for example, right?
That is a very good question.
Is it simply, I don't know, one string, which is one board representation under some domain-specific language, or is it?
I actually don't remember. I think we use a general embedding of these symbols. So we do have a mapping from the symbols to an embedding, and then it's on this embedding that the transformer operates.
I see.
Yeah, if I remember correctly, but I would have to double check the code. So that is the input, the sequence, and then the output is obviously dead or alive, binary prediction, also trained with just binary cross-entropy.
Thanks, Professor. I think I probably just missed a few details, but it seems a bit magical to me, this model itself, and it's a neurosymbolic model. Isn't it ultimately also a hidden Markov model, just a complicated one? Or so what's the difference between the deep HMM and your model distributed?
Let's maybe go back all the way to the beginning, because that is an important difference to show. And is at a high level, it's a Markov model, just like a hidden Markov model. The only really change that we do is that in a hidden Markov model, the latent state is hidden; it's an embedding. While in the Nessie Markov models, the latent representation is formed by relations. So stuff that you can operate on a logical level. You can, let's say, as an example, for our experiments, what would be in this S state of the Nessie map would be location of player. That is something that has clear semantics. You know what that means. And that also means that you can define logic on top of it. And if you define this logic on top of it, you can deduce other relations that just are part of your S state, your symbolic state. So you can operate on this state with a neural network because you can input and give those symbols as inputs. But you can also operate it on a logical level by just doing logical deductions on those relations.
Okay, so it's placing some structure over the hidden.
Yes. In the terms of Bayesian networks, again, you can see this S state as something that has its own Bayesian network structure. But only, again, instead of a Bayesian network, then we use this logic programming perspective.
Is there a distribution over the unknown states, or is it?
For the Nessie mems, yes. Yeah. So as I said before, an example would be location of the player that would follow a certain distribution. So in the case of a 5-on-5 grid, that would be a 5-on-5 categorical, because there are 5 possible states. Yeah. So we do put distributions over everything. Our model is a really probabilistic model. Yeah.
Performance-wise?
Yeah. Well, go ahead.
Yeah, so performance, I would probably.
Yeah.
How much does it cost?
For our experiments, the difference is not too big. It was not even double.
In terms of time?
Yeah.
Memory,
Yeah. More time and maybe, I don't know, the dimension of the knowledge. Yes.
Yeah. Well, so the dimension of the knowledge, I guess the biggest case we have here is the final one on the right. So 15 on 15 grids.
Yeah, but then the rules will be the same, right?
Yeah, the rules will be the same. Yes, of course, might have more ground instances of the rules because you have, for example, more enemies, more grids to reason over. But the rules are at a first order level the same. Now, computation-wise, in terms of time, I don't think even for those big cases, it took twice as long to do the prediction time of sequence to binary classification. Of course, we engineered this quite hardly, but you can make it work. The only hard thing you have to do is doing this initial compilation of the transition for the Rao black-hole-ized filter. But for that as well, we can use existing exact inference methods that are reasonably or actually very quick nowadays. Maybe as a sneak peek for the language modeling, because we are working on that and we have applied that to, let's say, an LLM and augmenting it with a couple of steps of reasoning at every time step. There it can go up to 3, 4, 5 times slower than a regular LLM, because we also cannot do some of the optimizations that LLM inference has, but it's still reasonable in a sense for now. Yeah.
Thanks for the talk. I just wondered if there's been any comparison to constrained optimizers. For example, I know this model would work on a partially observable entropy. So you embed logic by the constraints to your optimizer, and then it generates states forward.
Yeah.
Has there been much comparison to that?
No, so in this paper, we didn't compare to that at all. Now, you also say MDP. I'm not an expert in the constrained optimizers, but I imagine there are constrained optimizers for the Markov process case, because all of these experiments are not decision processes. They take interactions from a game that you can model as an MDP, but the task is a Markov process prediction in a sense. So I'm not sure if those constraint optimized would work there still, but we haven't compared to those in a sense. Yeah.
I guess the decision process isn't like strict in the sense that it has to be domination. It also states more. Yeah, I just wondered if that's
Yeah, no, but that would be an interesting comparison to see, because that would be something that tries to induce the constraints at training time. I'm not sure if they have any guarantees of constraint adherence. If they do, that would be super cool.
Yeah, it depends on your sort of that end optimizing platform.
Okay.
And it's another sort of solution to the reinforcement learning problem where people potentially end up reward function.
Yeah.
Compete with an extreme optimizing can also help with that.
Okay. Okay. Interesting. I will definitely look into that. Yeah.
All right, thank you.
Thanks.
I have a question. How many particles do you use?
A couple of hundred.
Only. Okay.
Yeah. Yeah, I think it's a couple of hundred.
Okay.
Maximally
During
1,000.
learning as well?
Yeah.
Okay.
Yeah.
Okay. And another question that I have, if you go back when the case when you had the constraint that you should not step over the last two columns, right?
Yes.
I want to better understand why for the generation the agent stays in its position,
Yeah.
right?
It's a bit of a detail, but so we added some, how to say, leak probability, that if there are no actions still available that satisfy the constraints, the only thing that you can do is stay where you are.
I see.
Yeah.
Okay.
So that there is
you added
no.
this kind of like additional
Yeah.
action that
Yeah.
is stay where you are. Okay.
Yes.
Could you say a bit for this language modeling cases, language modeling case?
Mhm.
How that compares to combination with fixed match, circuits, without
So we haven't done those comparisons yet, so I cannot say much, but at least
I guess more conceptually, like how
I guess in terms of gelato, if I remember correctly, where you learn an HMM to distill the LLM first and then use that to do the backwards propagation of future constraints. In that case, you have no guarantee that you're actually sampling from
Yeah.
the LLM distribution, because you have a part of this LLM and then a part that is your optimized model. Here, you would approximate the true LLM distribution. Approximate, of course, but
and in what sense is it approximation? Like approximation is only a certain context and
it's an approximation in the sense of it's a particle-based approximation, so a sampling approximation.
okay.
Yeah.
They should be closer to the works from Alex Lab and one from team, but also in spirit to the recent works by Karim, where he was sampling and using the pseudo semantic loss.
Yes.
Kind of similar in spirit.
Although there again, I think you have the fact that you don't have the same distribution again, so there is a bit of a bias there as well. Yeah.
It's hard to see also which kind of bias you introduce with particles, right?
Yes.
I mean, in the limit of particles, right?
Yeah.
If you have infinite particles, you let them do whatever, then you should be recover that exactly, right?
Yeah. Yeah. So you do have a soft or weaker guarantee of only a statistical guarantee that in the limit you will get to this distribution. In practice, yeah, you might not be, but at least it's unbiased.
All right. Other questions?
Any questions online?
Seems no for now.
Oh, wait.
Okay. So let's thank Lennert again.
Thank you.
For the people here and online for attending.
Yes, thank you for attending, everybody.
All right.